Hello, and welcome back to the course. So we're going to talk about slope fields today. So this is section 1.2 in the book, which you can get at this URL. It has just free PDF, or you can browse as web pages, or you can get an inexpensive paperback, which is probably the best way to support this project. All right, so let's get on with the show. So let's consider a general first order ODE. So we're saying that some function y's derivative is, well, some expression in x and y, right? All right, and we can't always find a solution y, right? We can't always solve this equation explicitly. But we can always at least figure out, just by looking at this equation, we can figure out sort of the shape that these solutions will take, what their graph will approximately look like, and a little bit about the behavior of such solutions without necessarily solving the equation. So that's what we're looking at today. So at each point x and y in the plane, right? So x is the horizontal axis, y is the vertical axis, right? The solution, if it existed, right? If we had, or if we could find it, right? Solution y prime. So if we are at a fixed x and y, right? Fixed point in the plane. We know what the slope of the solution would be, right? Y prime is supposed to be the slope that y has when we plug in x, right? So we know the slope, right? So maybe what we could do is we could draw a little bit, short line at that point, right? That's something that we know. We know the slope. I mean, we might not know exactly what the solution looks like, but we know at least at any particular point, we just plug in that point into our expression f here, right? And we get a slope. We get a number. That's the slope of the solution at that point. So we'll draw that little line. So then we'll do it for all points. Well, maybe not all points, but enough points to really see what's going on, right? So let's do an example. Suppose that our equation is this: y prime equals x times y, right? And so let's look at some random point. Let's say 1.5. So x is 2, y is 1.5, right? So the point is right over here, right? Now, the expression, this f over here is x times y, right? So x is 2, y is 1.5. So you multiply them together, right? And I get 3, right? So x times y is 3. So I draw a little line of slope 3, right? I'll draw it, fairly small, so that I can fit more of these in there, right? Now, drawing one is not enough. You really have to draw a whole bunch. So I'll draw even smaller ones over here, right? But I do it for some grid. I can do it for a finer grid or for a coarser grid. It's basically you generally use a computer to give you this, slope field. That's what it's called. And it's, you want to, the finer the grid, the more information you have, but then it's also the harder to see because it might be too busy. So, it's not like there's a best, best grid that you can do. But this is this one choice, right, that I made, right? So that's what it is. So that's what we did at each point, right? We looked at the point, and then we looked at what x times y was at that point, and then we drew a little line with that slope, right? So over here, right, it was that slope. I don't know, let's say over here it was, this slope. Over here it was just 0, right? Because if you look at it on the x-axis, that's where y is 0. So you get just horizontal, right? So here all these lines are horizontal. Well, similarly over here, when x is 0, we have horizontal lines, right? When we're in the first quadrant, well, both x and y are positive. So those are all positive slopes, right? They're all going up. Well, different slopes because they're different points. Those slopes are going to be different, but they're all positive. They're all up, sloped up. Same thing in here, right? Because we're multiplying a negative number times a negative number, and so on and so on. So over here we get negative slopes and so on and so forth. All right. So this is called a slope field. That's what this section is about. Slope fields, right? And we can do it, if you can evaluate this, on a computer, as long as it's some given expression, you can easily have the computer draw this. I mean, you can draw this by hand, but it's a bit annoying. You probably wouldn't do it for this many lines if you had to do it by hand, but maybe like for a 5x5 grid, you could fairly easily do it by hand, right? It would still take a while. That's why we have computers, right? But they can just, it's basically, sort of think of it as sort of graphing. It's a graphical representation of the equation, right? And so there's no, nothing needs to be solved here, right? This is, this is just done, right? We just draw this. All right. Now, given a specific initial condition, right? So given some x naught, we have that y is supposed to be y naught, right? Well, then we have a solution, right? We can actually, if we can solve, right? I mean, there is a solution even if we can't find it, right? But, let's suppose that we can find it, right? Then we could, plot these solutions in there. So, for example, here's a couple of solutions. So, for example, one where at 0, it's 0.2, right? That's actually this, this point over here. So that's this guy, right? This guy is going sort of, curved upwards, right? There's another solution here, one given for when x is 0, y is 0. So that's actually this guy, right? That's actually just y equals 0, right? And we can easily see that that's actually a solution here. Y is 0 because if y is 0, then y prime is 0. So both sides here are satisfied, right? And it's something at 0 at 0, right? So that's this middle line. And then if the negative if the y at 0 is negative, let's say minus 0.2, we actually get this solution, right? So you can actually see. Just by looking at the picture of the slope field, you can actually see that that's what the solutions should look like. I mean, these are the actual solutions. I had the computer, solve numerically and actually try to, draw the exact solutions. But you can sort of, maybe you can't see that that's exactly what they're going to look like, but you can sort of see that that's what they're going to look like because the solution is going to have to follow those little lines, right? So essentially, like if I start over here, you can see that, well, it's probably going to look like this, right? Because I just follow those little lines. And if I start over here, it's going to sort of look like, maybe that's not the best solution, the best drawing, but it's going to sort of look like this, at least sort of, a basic idea of what the solution looks like. I can see directly from the slope field, right? I don't have to actually have it, solved exactly, right? I mean, it's going to be hard to necessarily, tell anything very specific, but just sort of the basic shape, the basic behavior of the solution, I can immediately see, right? For over here, I know that it's going to go down, right? And then it's, then I can see that it's going to, do this. And, if I plotted this for a finer grid, I'd get more information. All right. So that's what the slope field is, and that's what you can sort of read from it. So let's look at maybe another example. So this is a simpler equation. Y prime is minus y. And well, here, for example, there is, this expression on the right-hand side, minus y. Well, it doesn't depend on x, right? So if you look on a horizontal line, right? So for example, where y is 2, right? Anywhere where y is 2, right? Anywhere here, right? Well, you can see that all those slopes are the same everywhere on this line. And maybe let me just draw this as a line, right? Anywhere on this line, the slopes are all -2, right? They're the same, right? So we can see that immediately from the fact that this right-hand side does not depend on x. It's gonna just be, I really just need to look on how far from the x-axis I am, right? And here, so we see that it's always the further away I'm from the x-axis, the the steeper it is. Either if I'm below 0, then it's steeper up, because if I'm below 0, y is negative, minus y is positive, right? And the more negative y is, the more positive y prime is going to be, right? And exactly the opposite up here, right? If the higher y is, right, the more negative minus y is going to be, right? Which is supposed to be the y prime, right? Now, a few solutions are also drawn here, right? These guys over here, right? They're just basically, I'm just following these little lines, right? I'm following the slope field. But you can see just from looking at it, you can sort of see their behavior, right? And it's clear just from looking at this slope field that these solutions, no matter where I start, they're gonna tend to 0, right? They're just gonna go and approach 0, right? Because whenever I'm above 0, I keep going down. Whenever I'm below 0, I keep going up. So just from looking at this slope field, I can tell you that whatever the solution is, as x grows larger and larger and larger, y, the solution, so y of x, will get closer and closer to 0, right? So for example, I know the limit as x goes to infinity, I know what y is going to be, right? I know that that's going to be 0. I don't even have to, I mean, here I can solve, right? I mean, it's just that's the exponential decay. But even if I didn't have that, I could immediately tell that that's what's going to happen, right? I'm going to be approaching 0 just by looking at the slope field, right? All right, so let's consider this initial value problem, right? So we have this general first order ODE and some initial condition y x naught equals y naught, right? Right. So there's a couple of questions. So first, does a solution exist, right? I mean, I can draw the slope field and look at it, but it doesn't tell me that really is there a solution, right? I can sort of, if there is one, I can sort of see what it would look like, but does one exist, right? Does it make sense, right? And sometimes we can answer this question by looking at the slope field. And is the solution unique, right? Now this is harder to check by looking at the slope field. Now, that might not be your first question about this, but it's an important question, right? I mean, we're probably starting with some real-world problem. You find a mathematical model that's supposed to model this real-world problem. Now, in the real world, well, depending on what sort of physics you do, but in Newtonian, classical Newtonian physics, right, it's everything's completely deterministic, right? So if I take a rock and I throw it at a certain angle, at a certain speed, it's just going to always land at the same spot, given everything, all the conditions being the same, right? Now that's because, well, the equation that, the differential equation that governs that, well, it has a unique solution, right? The trajectory is unique, right? I can just solve for it, right? It's not that if I solve it some other day, I'm going to get a different solution, right? I mean, it's always going to land at that same spot, right? Now, usually, if if you end up with, and it's possible that sometimes differential equations do not have unique solution. They might have a solution but not unique. If you end up in this sort of situation, it's probably something wrong with your model usually. So, what would it mean for it to have a non-unique solution? Anyway, let's we'll look at some examples, right? So the answer is usually yes to both questions. You have to there's to be something wrong with this f, right? And we'll see that it's called Picard's theorem. That's that tells you when is the answer yes to both of them. So it's most of the time it's yes, but not all the time. And it's you don't even have to it doesn't have to be really weird equations. We'll see some fairly simple examples where it's actually no, right? And it's again probably you have the wrong model if the answer is no. Right, so you have to. So you did something wrong with taking your original physical problem, the thing that you're trying to, the actual problem that you're trying to solve, and how you got to the mathematical model, right? So how you got this equation, right? All right. So let's see number one when it doesn't exist. So it's sort of the simplest. Simplest possible guy here. Look at, what about y prime is equals 1 over x, right? And let's look at this initial condition, right? Y at 0 is supposed to be 0, right? I mean, that seems not too bad, right? Very simple equation, right? You can even write it in a sort of more harmless way, right? I could multiply by x just to not have any denominator. It would be in a slightly different form, but x times y prime equals 1. I mean, that seems very reasonable, right? So, all right. Well, we can integrate this, right? I mean, this is an integrable equation, right? I can just, the right-hand side is just a function of x, right? And the integral is logarithm of x, the natural logarithm, plus some constant, right? Now, there is no solution when x is 0, right? I mean, that sort of makes sense. I mean, this thing is not defined. We're dividing by 0. This is not a, this f is in particular not a continuous function, right? I mean, it blows up. It goes, if x is coming from the positive side, it goes to plus infinity. If it's coming from the negative side, it goes to minus infinity. It's not even defined that x equals 0. So the equation isn't defined. The equation isn't, the right-hand side is not continuous. You can't even plug in x equals 0. It sort of doesn't make sense to ask this. And it might be, a little hard to see it from the second form of it, right? There's no division by 0 there, right? And from the solutions, well, you can see that you can solve it because logarithm is also not defined at 0, right? I can draw a whole bunch of solutions, and they all look like this. This is the slope field with the solutions, and we can see what they look like. But none of them are going to go through. X equals 0. None of them are going to be defined there, right? So it's impossible to solve this, right? Well, it's possible to solve the equation, but not with this initial condition, right? So not at that point. You can solve it, right? I mean, here we have some solutions, right? But maybe if you have that that x as 1 is 1, that's this solution over here, right? That one we can find. That one's perfectly y at, so when x is 1, y is 1, right? That one we can find. That's a perfectly valid solution right there, right? But at x when x is 0, no, we can't do. No matter what you've set y to, what you want y to be, there is no solution that where x equals 0 is anything. All right, so that's the first example. So now maybe a little bit more subtle example. So suppose my right-hand side now is this guy. So now it doesn't depend on x, but it's still very simple. It's 2 times the square root of absolute value of y, right? A very nice equation. Well, nice. Well, we'll see that it's not so nice, but it seems reasonably nice. And it's definitely continuous everywhere. The right-hand side is a nice continuous function of y. There's nothing wrong with that. And now we look at this initial condition. Now, here, we actually do get a solution. Just immediately, right? Just we guess a solution. Y equals 0, right? That's a perfectly valid solution. If we plug that in, y prime, right? If y is 0, y prime is 0. So the left-hand side is 0, and the right-hand side is also 0. We just plug in 0 under the square root. So that's a perfectly fine solution. Unfortunately, there's another solution. Well, there's actually infinitely many solutions, but here is another one. So you can have something that looks, it doesn't have a nice formula, but well, we can define it piecewise. It's a perfectly fine function. It has a derivative everywhere and so on, right? And it's basically, it looks like for negative x, it looks like minus x squared, and then so that side of the parabola, and then it's the other side of the parabola. It's x squared when x is positive, right? And we sort of glue those together, and we get a solution, right? And it still satisfies the same conditions and the same equation. You can check that it satisfies this equation. All right. Well, that's sort of bad, right? We get this 1 point. We get at least 2 solutions, and you can do more solutions, right? You could have a solution that's just for negative x, it could be 0, and then it could be x squared, right? Or maybe you could get this you can move this parabola over here. You can shift it so that it hits the x-axis over here. Then it goes a little bit along the x-axis, and then it goes up to x squared. Yeah, that's another solution. So you can construct a whole bunch of these solutions. Then they're not unique, right? And you could have another one over here. It could go on for a while and then move up, right? So there's lots and lots of solutions. But there are solutions. Solutions exist. We just can't guarantee that they're unique. Okay. So you might be sort of saying, well, that's all bad. Those were fairly simple. Maybe the first one is kind of easy to tell. It's 1 over x. Things blow up. Maybe that's easy to tell. But over here, maybe it's not so easy. But it's not too bad. There's there's hope left, and the hope is Picard's theorem. Right? So Picard's theorem says that if this f is continuous, so you need continuity, but you need more than just continuity. So you need a continuous function, and you want the derivative in y, so the partial derivative with respect to y. So you take this expression f of xy, and you differentiate it in terms of y, and you want that to be continuous, right? So you want both the function, the f of xy, to be continuous, and the y derivative, right? And you want it to be continuous at least nearby x naught, y naught, right? You don't want it, near that point, so in some small range of x's and y's around this point. You want these two guys to be continuous, right? And then a solution to this general first order ODE exists. I mean, it's not going to always exist for all x, but at least for x in some interval, right? And we already saw this before. And it doesn't just exist, it is unique, right? Well, where it exists, right? Okay. So for example, these guys, this or this, do not satisfy the hypothesis. In the first guy, what's happening is that the f is not continuous. 1 over x is not continuous at x equals 0, right? So we're failing this hypothesis. On the second one, okay, so the 2 times the square root of absolute value of y, that is a continuous function of y, so continuous function of x and y, right? However, if I take the y derivative, I'm going to get 1 over square root of y, essentially. And so that is not continuous, right? That blows up, right? So this, and actually, the derivative doesn't even exist at y equals 0, right? So this guy doesn't exist, right? And and even if you just do it where it exists, it's not continuous, right? So it's neither of those examples satisfy that hypothesis, but that those hypotheses are fairly easy to check, right? So, for example, let's do an example that we did before. Like, for example, y prime is y squared. Now, that's y squared is a continuous function, and the y derivative, well, that's 2y. Yeah, that's nice and continuous near any point, right? So we can apply this initial condition, right? Really any initial condition, and we can solve. We're gonna have a solution, right? Now, if a is 0, so if this constant a is going to be 0, then y equals 0 is the solution, and it exists for all x, right? Because it's just 0. No matter what x is, it's 0, right? So there's nothing, it doesn't blow up or anything. But if a is not 0, then we saw that the solution was of this form, right? 1 over c minus x, where c was some constant, and we pick c so that we satisfy the initial condition. So in this case, if y at 0 is supposed to be a, then 1 over c minus 0 is supposed to be a, so 1 over c is supposed to be a. So you just, so c is 1 over a. So we get, well, c is 1 over a, and we get that the solution is this guy, right? Now, notice something about this. It blows up, right? And we saw before, we saw what happened here, right? We saw the graph of this, right? It's basically like 1 over x just shifted. Well, 1 over minus x just shifted. But it's, for example, if a is 1, right, it blows up when x is 1, right? Because then 1 over a is 1, so it's the solution is 1 over 1 minus x. You should use a different pen for this, but then this thing is just 1, right, for simplicity, and that blows up when x is 1, right? So the solution only exists for x less than 1. So it doesn't exist. You can't say it's going to exist for all x, right? So Picard's theorem does not tell you that it's going to exist wherever, for all x where this is satisfied. It just tells you that for some interval of x's, right? For some interval around x naught, right? You are going to get a solution, a unique solution, right? So for example, here, for some interval, well, it's this entire interval where, from minus infinity to 1, right? So that's an interval where 0 lives inside that interval. And we get a solution there, and it's the unique solution, right? So you might not get it everywhere, but we get it at least locally, we always know that we can get a solution. So that's the power of Picard's theorem. It tells you exactly when you have solutions, right? And it's easy to check. All right, now, if we choose a different initial condition, which really means that we chose a different point, that could be, that range of x's could change, right? So if a was 100, then 1 over a is 0.01, right? And so the solution blows up at 0.01, very close to our initial point, x equals 0, right? So the solution only exists right? I mean, anywhere from minus infinity, but in the positive direction only exists up to 0.01, right? No longer goes up to 1 as before, right? Now it goes only up to 0.01, right? So, yeah, but it's still, that's some interval, right? That's all Picard's term says, right? All right, so so that's it for today. So see you next time.